So this is my review of chapter 23 of differential equation and exponential of a. And by far this was the most difficult one compared to the other one. There are 5 points that I would like to review here. The first one is the main formula that we are learning, that du over dt is au, and the stability of the eigenvalue. And the third one is another way to expanding u of t in terms of the exponent to the e to the power of at and e to the power of lambda, big lambda t, and then expanding the e to the power of at in terms of the infinite series, and how to transform the second and third order into this form of du dt over au. So I will divide maybe this session into 5 parts. So I will discuss the first one, which is the du over dt of au. So this equation, the solution of this equation is the u of some constant e to the power of lambda t x, where the x is the eigenvector of a. And this formula right here, the one that we have been learning so far in this eigenvalue vector chapter, still valid. In fact, that's what we want to see here, which is the power of the eigenvalue and eigenvector to help us solve this kind of formula, the differential equation, whereas in the previous lecture we have the difference equation. Okay, so before moving on further, there are some things that I would like to, some prerequisite that I would like to discuss here. A couple of them. So let's say I have my function of u in terms of t, which is e to the power of lambda t, and then let me derive this du over dt. And how you derive this one is that you just derive whatever in the power here, which is right now I have the lambda, then I just write the rest as it is, and then so I end up with the du dt of lambda u. Okay, so you see that this derivation of du dt lambda u has the solution of u is the exponent of to the power of lambda t. Okay, and but actually see here, I'm assuming that here the constant of to e is 1. So let me write e in a slightly different terms. So I have du over dt here. C is just a constant, it doesn't have anything of t inside. This is only the part that have t, so I just pull it down, derive this one. And again here I have c and e to the power of et, and I can rewrite this one as c of, nope, that's not correct, lambda of u. See, so although I start with a somewhat different, slightly different formula, but this is just a constant, so it doesn't matter. So we always end up with this du over dt equals to lambda u. And let me start with 1 again. So see here, the u of t is c e lambda t, and then I have this x here, the eigenvector of ax. So let's see how that goes if I do the same thing as what I just did. U of ce power of lambda t x. So once again I derive them. Again, so these two are just a constant. Okay, doesn't have anything of that coupled to t inside, but only this one have. And then you see again that I have this term here, the x and c. So this is equal to u, right? So I can rewrite this again to du dt is the lambda here, and the rest of them, the u. So let me underline that lambda. Okay, so this is here, and the rest of is u. Okay, so it also ends up with the same thing here. You see these three are the same. So we can say confidently now that if you have this form, so how do you find a solution? What is u here? So u is this one, or this one, or this one. Okay. And in this case, we want to attach this x to this equation because we want to tie it with the what we have learned so far, the eigenvector and eigenvalues of A. Now let's see how it plays a part. So let's see here. Okay, let's see. I have this form of du dt and au, and to prove that u is the correct solution, u of ce lambda t x is the correct solution to this when ax is the lambda x. So let me plug in eu to here, and let's see if I can see the connection here inside. Okay, so let me do that. So d of dt and c tx is a u. Okay, and then I derive this one, so exactly as what I just did here, which is we end up with and then the x. Okay, and then let me also plug u here, so I got ce to the power of lambda t x. Okay, now I can cancel this term, e to the power of lambda t. I can also cancel the c, and let's see, I end up with the lambda x equal to ax. So this proves that this one is also valid here. So that's one way. That's how also the Professor Strang prove it, and then I guess that's enough for proving that the solution to this term, if we got this term, if we have a system of u and we have the matrix that describe how that system behave, we can have that solution by doing this. And x is the eigenvector, and lambda is the eigenvalue of a, and c is the constant that define each component. So let's see a quick example here. So I will read you the example what Professor Strang had in his lecture. So before that, I want to mention one little thing. So you know here there's a ut. So actually the terms u of t here, it will be used interchangeably a lot with the ut. So I will just want to remind that u of t is equal to u in this case. Most of the use case here that we will see, when we say u, we will implicitly also mean that it is u in the function of t, and I just want to remind that quickly. Okay, so let me put that aside here. T is also equal to u in this case. Okay. So say we have two equations of u. So u of the u1 accent is the u1 times 2 u2, and then u2, the derivative of u2 is u1 minus 2 u2. Okay, and then the initial state of u of 0, which is the t at 0, the initial state is 1 and 0. Okay, and then let's solve u. So what is u? Solve u. Okay, so first is we should transform all the information that we have into this form right here. So you see a square here, and when you see this equation right here, you should immediately think of the matrix A, the square matrix that we have here. So, and then you see that we have the u1 and u2 here, so let's create a vector of u, which is u is the u1 and u2. So a system that has two functions of t that kind of depends on itself and the other. So u1, it depends on u1, and u2, I'm sorry, my u kind of looks like v here, but we are not discussing v at all. These are all u. Okay, so when we set du over dt, it's actually just the d of how to write it properly. So u1 u2 over dt, so this will be like u1 and u2 accent, or the derivation of them. Okay, so we have we can express this in terms of this, which is will be, because we have our vector u here, which is u1 u2, this will be our vector a times the vector of u1 u2. So here is our vector a, this is our vector u, and this is our u as first order of u. Okay, so this is exactly what we have here. Okay, let's see that, compare that. Okay, we have that exactly as it is, and now we need to fill this matrix A and just follow along with this. So we have -1 2, and then we have 1 -2. Okay, nice. So the next thing here is to find the eigenvalues and eigenvector of A. So always in this chapter, you know, if you have been also following along, whenever you see a matrix, a square matrix, we need also to think of the eigenvector and eigenvalues. So let's find them. Well, just we'll do the usual case here. So this will be, and the determinant of them, let me write this, determinant of here is equal to 0. Okay, okay, and then if you do the operation, I'm gonna skip here just to speed up a little bit. You will have the eigenvalue of 1 is 0 and eigenvalue of 2 is -3. Let's do a quick check. So the sum here is -3, which is exactly what we see in the trace here. -1 plus -2 is -3. And also we know also from previous lessons that the multiplication of them is 0. So if you see, if we multiply here -3, oh sorry, +3 and then -3, so we get 0. So that match exactly as we expected. So I'm going to remove them quickly. And then we have the eigenvalues now. Eigenvalues. And now we look for the eigenvector. Okay, let me just shorten it up by writing E vector here. So let's do that quickly. So you will have by the first one you have just matrix as is it is, and then the x1 will be the 1, and then you need 2 here. Okay, so you have x1 is 2 and 1, and then if you do the second one, the what is it, -3, then you will have wait, I need to change it first. Okay, 2 2 1 1, right? Because you -1 and -3 2. Okay, yep, 1, and this will be -1 1, or it can also be like -1 1 here. It doesn't matter. It just it's still in that line. It's just has a different sign. That's okay. So let's write that down here, 1 -1. Okay, and let's remove this one. Now we are ready to use what we are learning here. We can put it in this general formula term, in this solution terms. Okay, so you have the u. Now remember, I said before the ut equals to u, so I'm just going to write it u here, and have some constant, and then I can write the general formula here equal to the first eigenvector, okay, plus another constant term, second eigenvalue, second eigenvector, okay. So this is the x, and this also x, okay, cool. Now let me put that down. So I have the 0 t, and x1 is 2 1, and I also have c2 e minus 3 t 1 minus 1, and this actually is 1, right? So let me just simplify that into this form, right? Because 0 t 1, okay, cool. Now I have well, not yet actually. I already write this down, but I still need to find this the constant, right? The c1 and c2, the constant that accompany each eigenvector and the e to the value to the power of lambda t. So how do I get that? Is by plugging in the initial vector. You remember, I think I delete them down here, but there's an initial condition of u when it is at t0. Let me delete this because we don't need this anymore. Okay, so t0, it is 1 and 0. So this is u at 0. Okay, so let's plug it down. So remember, I will use this interchangeably, so this is also like ut. Okay, so let's write that down here. Ut c1 to 1 plus c2 e minus 3t 1 minus 1, and at t equals 0 it will be equal to 1 0, and the rest follows along. So t also equals 0 here, so 1. So we have these two equations with two unknowns, so we can get the c1 c2. So c1 here will be 1/3, right, because c2 will be -3. So let's quickly test it. So we follow along in the first dimension. 1 equal 2/3 plus 1 equal, I'm sorry, this should be plus, right? Yep, it should be plus. So 1 equal to 2/3 plus 1/3, so that will 3/3 1, and 0 equal to 1/3 minus 1/3. Okay, match. Okay, now we have the complete solution. So let me delete this one right here, that one. Okay, now our ut is the following. Ut is the 1/3, which is we got here. I'm sorry, let me write down. c1, 3 is also 2/3. Okay, 1/3 of e 0t. Let me just delete that because it is 1, and the first eigenvector plus the c2, right, and e to the power of -3 th, and second eigenvector here 1 minus 1. Okay, now we got our answer. The solution of this formula, of this equation, du over dt au, is equal to this ut. Okay, now remember that ut here is actually the u1 and y2. Okay, yes, so I think that's it for the first part. So here is actually what is really powerful for this. I'm sorry, I'm forgetting one thing, is that by doing this eigenvalue and eigenvector, actually you can see what is happening in the system, because what happens as t goes to the infinity, right? So as t goes to infinity, we have learned in the previous lecture also what only affect the system is the lambda, and here we have the lambda here, and the other lambda is 0, so it doesn't matter, and the eigenvector will still be the same, right? So if I say ut like 1000, what will happen is the system will go into this equation, and this will be 0. So why? Because if I divided this term, so 1 over e to the really big number, like 3000 or something, this will be really small, and it doesn't have any value in our equation. So it will go into this steady state of only the first component of what we have in our original a. Our a, again, just to remind you guys, is this one. I mean the first of the eigenvector. A bit sloppy, but sorry guys for my mistake, but that is it for the first point. So I'll see you in the second part.